In December 2024, NASA's Parker Solar Probe flew just 3.8 million miles from the solar surface. Traveling at 430,000 miles per hour, its front heat shield reached nearly 2,500 degrees Fahrenheit, while its scientific instruments operated at room temperature. Space is a vacuum, meaning traditional heat transfer by conduction or convection does not occur. Thermal energy hits the spacecraft almost entirely as intense electromagnetic radiation. Near the Sun, this radiance is nearly 500 times stronger than what hits Earth's orbit. Popular stories claim the probe survives temperatures of millions of degrees in the solar corona. In reality, while coronal gas particles move fast enough to register high kinetic temperatures, the gas density is so low that very little thermal energy actually transfers. The real threat is direct sunlight radiating onto the hull. Without protection, intense radiation would vaporize metal electronics in minutes. In 1958, astrophysicist Eugene Parker calculated that high-speed plasma continuously escaped the Sun, proposing the concept of the solar wind. NASA planned a mission to study this solar wind for 60 years. However, space agencies lacked materials capable of enduring the thermal radiation while keeping payload instruments cool. Early concept designs from the 1970s required complex liquid coolant systems that proved unreliable. Engineers at the Johns Hopkins Applied Physics Laboratory in Maryland solved the problem without active liquid cooling. They engineered a passive thermal barrier that relies entirely on material physics, reflecting almost all incoming solar light while blocking conductive heat from passing through. The resulting craft launched from Cape Canaveral in August 2018. It relies on Venus gravity assists to gradually tighten its orbit around the Sun. Each perihelion pass brings the probe deeper into uncharted territory, testing its structural design to the absolute limit. The primary defense mechanism is an 8-foot diameter shield known as the Thermal Protection System. Despite its massive size, the shield weighs only 160 pounds. It sits mounted on the front of the octagonal spacecraft body, completely shading all primary systems. The heat shield consists of a high-tech sandwich structure 4.5 inches thick. The outer layers are made of superheated carbon-carbon composite material, similar to what is used in modern high-performance aircraft brake discs and hypersonic nose cones. Between these two carbon composite sheets lies a core of carbon foam that is 97% empty space. Because carbon is an excellent structural element but a poor thermal conductor when formatted into porous foam, heat travels through it extremely slowly. To manage radiation, engineers applied a specially formulated white ceramic coating to the sun-facing side. This alumina oxide layer reflects over 99% of incoming solar energy. The small fraction absorbed is radiated back into empty space from the outer surface. This thermal gradient is one of the most extreme ever engineered in spaceflight. While the front face reaches 2,500 degrees Fahrenheit, the temperature directly behind the shield remains around 85 degrees Fahrenheit. That is roughly comfortable room temperature for the instruments. Testing this shield on Earth required unprecedented laboratory environments. Engineers exposed thermal samples to concentrated solar simulators and specialized particle accelerators at Oak Ridge National Laboratory. They confirmed the ceramic surface would not degrade, flake, or evaporate in vacuum. If the ceramic paint were to flake off during flight, the exposed black carbon beneath would absorb solar heat instead of reflecting it. That added heat load would quickly burn through the foam core, destroying the spacecraft chassis within minutes of exposure. Most instruments on the probe sit safely inside the dark thermal shadow cast by the shield. These include the field's magnetic suite, the integrated science investigation of the Sun, and the wide-field imager for Parker Solar Probe optical telescope assembly. However, one instrument must extend outside the protective shadow to capture direct solar particle samples. The Solar Probe Cup, part of the SWEAP instrument suite, sits in the full glare of sunlight to catch charged ions and electrons flowing from the corona. Because it cannot hide behind the heat shield, the Faraday cup reached temperatures exceeding 1,800 degrees Fahrenheit during close solar flybys. Standard electrical wire insulation or common copper conductors would instantly melt under these conditions, rendering the sensor entirely useless. Engineers constructed the instrument grid using refractory metals with extremely high melting points. The cup grids were micro-machined from solid sheets of tungsten, a metal that melts at over 6,100 degrees Fahrenheit. Electrical wiring was fabricated from pure single-crystal niobium. To prevent short circuits at high temperatures, designers used synthetic sapphire crystal insulators instead of plastics or ceramics. Sapphire retains electrical resistance even when glowing red-hot, allowing electrical signals from captured ions to travel back to internal computer hardware. During pre-launch testing, engineers placed the Faraday cup inside the solar environment simulator at the Smithsonian Astrophysical Observatory. They blasted the cup with tens of thousands of watts of solar radiation while firing ion beams directly into its tungsten collectors. The cup survived hours of continuous exposure without signal degradation. It proved that scientific instruments could gather direct plasma samples while exposed directly to white-hot solar conditions, providing the first direct measurements of the corona's physical environment. Even the best heat shield is useless if it points in the wrong direction. At perihelion, communications with Earth take over 8 minutes each way. Ground controllers cannot manually steer the spacecraft, so the probe must manage its orientation entirely autonomously. To maintain precise orientation, 7 solar limb sensors are mounted around the shadow margin at the rear of the probe. These small light detectors sit right at the boundary line where shadow meets intense direct sunlight behind the heat shield edge. If the spacecraft drifts by as little as 1/10 of a degree, direct sunlight strikes one of these edge sensors. Within milliseconds, the central flight computer detects the light pulse and commands reaction wheels or hydrazine thrusters to correct the orientation instantly. The probe relies on solar arrays for electrical power, but these arrays also face thermal limits. As the probe nears the sun, the solar panels retract behind the heat shield, exposing only tiny wingtips to generate required electrical power. Liquid water circulates through microchannels built directly into the solar panel structures. This heated water pumps back to radiator plates mounted in the shadow of the heat shield, dissipating thermal energy into the dark expanse of deep space. This closed-loop cooling system uses pressurized liquid water, keeping the solar arrays under 320 degrees Fahrenheit. It is the first time water cooling has been used on an interplanetary space mission, balancing high thermal intake with passive radiative cooling. Every component must operate without human intervention for days at a time. The autonomous software continuously runs health checks, ensuring that no mechanical failure or attitude error leaves the spacecraft body exposed to the direct glare of the sun. By maintaining this delicate thermal balance, Parker's solar probe has unlocked long-standing solar mysteries. In 2019, data revealed S-shaped bends in the sun's magnetic field lines, known as magnetic switchbacks, which reverse orientation in a matter of seconds. Before Parker's flybys, scientists believed these magnetic switchbacks were local atmospheric anomalies. Measurements confirmed they originate near the solar surface, whip through the plasma, and release massive bursts of energy that accelerate the solar wind to supersonic speeds. The probe also identified the boundary line where the sun's atmosphere ends and space begins, called the Alphane critical surface. In April 2021, Parker became the first spacecraft in human history to officially cross this line and touch the sun. Inside this region, magnetic fields control the movement of solar plasma rather than gravity or pressure. Parker's instruments measured plasma densities and magnetic field strengths that matched theoretical models proposed by Eugene Parker 6 decades earlier. In late 2024, the probe completed its closest planned pass, flying inside 4 million miles of the photosphere. Operating in an environment where solar radiation is almost 500 times stronger than at Earth, all payload systems continued functioning normally. The probe will eventually run out of hydrazine fuel needed to drive its steering thrusters. When attitude control fails, solar radiation pressure will turn the spacecraft, exposing its unshielded instrument body directly to raw, unmitigated solar light. Within hours, the carbon shield will drift away, and the craft will disintegrate into space dust. Until then, it continues flying silently through white-hot solar plasma, sending home high-resolution data from inside the atmosphere of our nearest star.